background. Our last presentation and demo for this afternoon is going to be from Dr. Dan De Laurentiis and Dr. Jitesh. I'm going to get your last name wrong. I'm so sorry. Panchal. Thank you. Come on.
Wait, his name is easier than mine. Okay, let me get the right presentation up here. Oh, I heard the staff. Can I do that? Okay. Here we go. So, how's everyone doing? Yeah. It's been a long time, right, since we had the 9 to 5 face-to-face meeting, right? No 20-minute dog walks in the middle. Dinesh, I'm looking at you. No 30-minute go watch a Seinfeld episode. I kind of know Dinesh's tricks. But it truly is great to be here, and Jitesh and I are just so excited with what we have to share with you. I'll say to get started that Jitesh and I are leading actually 2 projects in ERIC. In the ERIC currently, those are fairly recent starts, and so our presentation today is mostly about recent things that have been accomplished in the general area of mission engineering and advanced decision making to support mission engineering. But we're really excited about the task we have kind of supporting Nikki Abbott in one of the tasks on basically a prototype for a decision support framework for mission engineering. And you heard mentioned earlier from Chris O'Donnell about the IAPRs, the Integrated Acquisition Portfolio Reviews that are being developed, a process to execute those. And so our project, according to Nikki, is really critical to develop a prototype to make that process as rigorous as possible and to have the decision analytics to support that. Second activity, also with Nikki as our sort of sponsor and main monitor, is looking at sort of the life cycle implications for acquisition for additive manufacturing applications. And certainly Jitesh is critical to both of these tasks, but especially in that additive task, really looking forward to uncovering some nuggets of, what's hiding behind the curtain, if you will, in terms of life cycle and acquisition decision support in an additive manufacturing context. Great upside opportunity for sure, but we're looking to find out what some of the implications might be. So, and then, of course, in the middle here, we'll have a couple of demonstrations, both of which you'll get a much better version of if you go outside. And we have our wonderful postdoc and graduate student, Jitesh Mal and Prajwal Balasubramani, here with us. And so their tip jar will be out shortly out there. And please support them. Okay, so as Jitesh and I were sort of thinking about how to do this and have something that looks like demos but also kind of convey some higher level messages, we decided to start out, before we get into the 2 specific examples, to give a little perspective on mission engineering, and in particular, one slide at least that I have that will talk a little bit about how academics sort of need to translate some of the needs, the analytic needs in mission engineering, to things that academics can understand so that we can develop a broad and effective team of researchers. I can say that we actually did that very well, I believe, for the 2 tasks that I mentioned that have started recently in the ERIC on mission engineering. We have GTRI, Virginia Tech, Stevens, and other researchers at Purdue besides Jitesh and myself in those tasks. And so it's really been a nice mapping exercise to make sure we have the right teams. So before I do that, stealing slides is the greatest form of flattery, so I give credit to Judith, who's here. Judith, look up. I stole one of your slides. Okay. Now, I also see that Phil's name is mentioned here, so I don't know if Judith stole from Phil, and then Tracy and Monique. So anyway, there's enough that I've stole from to go around here credit. But I really thought this is, of course, a very nice bottom line up front slide about what mission engineering is. As you all probably know, given that I'm on the stage, the word and the term system of systems will come up a lot. And certainly, I've come to understand, in a richer sense, how mission engineering is sort of composed of which system of systems and how do we put them together in the mission threads that we have to examine. So I think we have a good basis in mission engineering. But I really felt that I needed to educate myself better on what the department is thinking about across the mission engineering space. And actually, I had planned, if I had 80 minutes instead of 40, to really try to dig into what each of the services and OSD, R&E, and ANS say specifically about mission engineering in their contexts. But there wasn't enough time to do that. So I did pick up at least on the mission engineering guide that came out, I guess, last year around this time from the R&E side. And I really thought it laid out, as many of you know, a nice process, a methodology for mission engineering. And it showed how the outcomes of mission engineering, support acquisition decisions, not just technology-based, R&E focused decisions, and a whole host of other things. And actually, I felt that the overview of the methodology here is kind of a good baseline for us to think about this decision support prototype that we have, because really it covers the gamut of all the key things we've talked about, from data and assumptions on the front end, context, do you have the right data to define the missions that seem to be important to the warfighter, all the way through the analytics and displaying and communicating those analytics as well. So again, by the time I've been speaking, you probably have read the words that you may already know. But again, in the center of some of these mission engineering definitions is this holistic approach to guide decisions, and I think that's the key. And so now for a little science. So that's sort of the requirement of the practitioners, need those kind of mission engineering outcomes. But when I try to talk to some of my design theory colleagues and everything, we have to start translating these into, these are, and we also need to educate the practitioners, these are incredibly hard problems. These are complex, hierarchical problems in which complexity arises in just a variety of forms due to the design and off-design interactions between the components, the presence of multiple types of interactions, and then, of course, if we apply the system of systems definition here, each of these little boxes will likely be owned and operated by a different organization that has their own unique and private purposes for those systems, as well as wanting them to share in the success of a mission. So we really kind of use concepts like this to sort of help us do the mapping between some of the science and engineering design theory that we need to bring to the table. I'll take 20 seconds just to give you a little PowerPoint fun story. So most of what I do, of course, is in the aviation, aerospace, and defense sector. I once had a project with John Deere, and I had this slide, which they loved in a previous version, kind of like that looked like this, but I changed the colors at one point, and I made all of the boxes, especially the ones on the right, in red color. And all of a sudden, they hated this slide. Who can tell me why they hated this slide? John Deere is green, and their biggest competitor is red. And I had these little boxes on the right-hand side in red, and they look like tractors, right? Those little red. So anyway, a little story in the ways you can get in trouble if you're not an effective communicator by knowing your audience. So I learned my lesson the hard way there. Okay, so my last slide in this introduction on perspectives. Of the many mission engineering challenges that are out there, especially for those of us developing methods and tools, these are two that we've kind of focused on. And so the two reasons I wanted to present this slide is to sort of highlight these two, because the demos, sort of map to them. But also, if you look at some of the sub-bullets, again, there's really a rich set of progress that's been made in the design engineering, systems engineering methodologies and tools, et cetera. And many of those, if I look back at the CERC portfolio, which I often do, over the past 15 years or so, you can see here things like set-based design, design under uncertainty, robust portfolios, flexibility, gaming, et cetera. There's really more power than we sometimes give ourselves credit for that's out there, but the key is, again, mapping and tailoring these to the effective problem. So the first one, clearly, especially for our current sponsor, Nikki Abbott, and the IAPRs, how can we use mission engineering and build decision support in an acquisition context for mission engineering? And clearly, this problem kind of does center very squarely on designing robust portfolios, because that's what you pick from when you're putting together capabilities against the missions and the mission threads, is the portfolios, and these portfolios are broadly managed and populated across the services, et cetera. And so there's really significant uncertainty, and so the robust decision-making is key, and we'll have a little example of that. And then the second, designing future missions, is also a tough problem, right? If you look at the beginning of the guide, as well as things you already know, this is tough. What are the missions of the future is just as important of a problem, since it's there at the very beginning, and so it's also an imprecise science. And so even conceiving what the missions are and then thinking about the technologies that need to be developed and acquired is also a difficult problem. And so there's a lot of progress, I think, in the AI/ML world, and Jitesh will talk about a project we've performed in that vein, as well as an increasing focus on flexibility and adaptability, right? So you know you're going to be wrong on the missions that you project into the future. So are there architectures that seem to do well on that baseline set, but also are very small changes away from also performing well on adjacent missions? These are the kinds of outcomes that we need to look at. I don't know, I just put this last bullet there. Some of you may know the Office of Net Assessment in the OSD, and sort of the legacy of Andrew Marshall and that approach of really looking at the strategic interactions and the consequential effects of asymmetries. And I really was reading more about that again recently, and again, the work that Jitesh is going to talk about on this notion of a game and balancing and imbalancing a game as a metaphor for finding missions that we will always win in the future was interesting connection for me. Okay, the two exemplars, I'll go a little bit quicker here, but I wanted to set the stage. I'll talk about the first one on decision support and portfolios and mission engineering, and then Jitesh will cover the second one, and then we have just a little snippet of work from others, including some in the room, that we want to end our presentation with. Okay, I already warned you, if it's a Dan DeLaurentis presentation, I'll mention system of systems. And they're so hard that it makes even the monitors and the display system freak out. I think this happened in Bill's presentation far earlier because he deals with more complex problems. But oh, I thought it might be getting better, but it's not. So, like Bill expertly did, I'm going to keep talking for a while until, oh, there. Again, I think a great success story and sort of, in particular, a success of how a lot of what Eric needs and wants to get done is leveraging what's been done in the CERC and what will be going on in the CERC. So this is all one big happy family. But many of you are aware that the Purdue team developed a system of systems analytic workbench to basically be that analytic kind of place to go when you have a system of systems problem to develop. And again, we work very closely with Judith and colleagues on developing this. And on the right-hand side, you see a number of tools we developed. And again, one of the nice things was that each of those tools, also behind them was a PhD student that became a PhD holder, and many of those folks are off doing great things now. And so this toolbox and the analytic workbench concept has been transitioned to a number of folks, including additional projects through the CERC and now ERIC. So here's just a little more of a pretty picture about some of those tools that I mentioned in the gray box on the previous slide, some of which I've mentioned already in terms of flexibility, dependency analysis, etc. But the particular one that I'm going to show here, and it's part of the demo that the team will show out, is the concept of the robust portfolio optimization. What is a portfolio approach, and what is a robust portfolio approach? Well, again, the family of mathematical programs, which is basically what these are pretty well known, and so we're tailoring them and innovating by tailoring them, but the mathematics of how to do a variety of different formulations for a robust portfolio problem is already there. And of course, the key concept is, just like you all perhaps do with your stock portfolio, you're looking for the basket of stocks and other securities that will give you the best return for the given value of risk that you're willing to accept. And so we're looking at the same problem here when we're developing a mission or a set of capabilities to support a mission or a system of systems. And so that's the concept behind the portfolio approach with robustness. Just the other thing I'll add here is, of course, it's not just what's in your basket, and in many ways, the stock example is not as good here because there's perhaps second and tertiary effects only between the securities. But in a portfolio of systems meant to operate as an SOS, as part of a mission or a family of missions, all these possible relations between the components are extremely important. And so you'll see in the demo, and it won't be very sexy here, you're going to see what looks like an Excel sheet because one instance of the workbench does use simply a set of Excel sheets to express the systems, the capabilities, and the interactions. But there's a magic to that, right? When you're trying to teach someone how a tool works, if it's a good person who wants to build trust, they want to use it themselves. And throwing a very large database at them that they can't even understand how to use that has been an impediment. So we have automated ways to develop these problem inputs, but the demo will show you one with an Excel sheet. Okay, so just before I get to that demo, again, the analytic workbench has found new life in several other projects. One I want to call out here because it has the genesis for the demo that you'll see is work we did again with Phil and her team looking at decision support for MOSA, Modular Open Systems Approach. And it really was kind of important that this was developing at the same time, especially as Mark Blackburn's work, because part of the motivation of the project was for programs to actually have some tools to express what the law was requiring them to express, which is justification for modularity decisions. But really, as we got into this particular decision support framework, there were some really powerful insights about exposing what were some of the opportunities and potential perils of choices on modularity and the like. So these boxes here just show some of the sequenced ways we developed inputs and used some of the tools in the workbench for that. And so here's a snapshot of some of the user interfaces we developed for this, and you'll see these at the very end of the demo here. So could you play the YouTube video? Now there's lots of interesting things you can find on YouTube, but this is going to be number one here in a short amount of time. Of course, right now it's private, right, Jitesh? Yeah, okay. So I'm your narrator for this, and so again, I highlighted on the previous slide those different constraints and inputs that relate to which systems can do what in terms of capabilities, which systems require a resource from another system, which systems have to be present in a particular problem, which systems can't be present if another system is present. So all of these logic and some of them numeric real valued constraints are essentially important to represent in the inputs to the decision-making problem. And again, not really shown well here. This is a spacecraft example problem, but in this sort of larger multi-domain battle scenario that we had also, there was ways to represent the uncertainty and also the options for choosing modular systems versus non-modular systems in some of the components. So without watching it, I tried to talk long enough to catch up on where we are, but there's the must-haves. There's the ones that require mandatory presence of another system. Can't live without. You see, by the way, the application here, one of the organizations that's leveraged this framework is NASA and some of their space exploration architectures. So that's been very gratifying. So here, once you get your input set up, we go to your graphical interface here to actually set up and launch the particular problem that you want with particular selections for certain designations, including your risk aversion that you just saw there. And we probably need more zeros for the cost in some of these examples in the real world, but they're kind of utils values right now. And you can put different weightings on the multiple objectives that are involved in the problem. And you please wait, and you get a family of portfolios. Columns 1 through 8 represent feasible portfolios that actually fall on the Pareto frontier. And there it is right there. So again, you can make decision-making trade-offs between can I live with the increased risk of this higher performing portfolio for a certain mission area. And I think we're almost done here. So after portfolios are generated, you can visualize the architecture behind those portfolios, as well as you'll see in a moment, using a second tool in the workbench, this SODA tool, Operational Dependency Analysis, that helps you analyze what if some of these systems were degraded by a certain percent. How does that propagate through these relationships and impact the value and the outcome of the portfolio? And so that's also been an important capability. There's the SODA tool as well. All right. Jitesh? Yep, you're on now.
Awesome.
Yeah.
Thank you, Dan. So this is an overview of a project that we just finished like 2 days ago. So we had, this is funded by DARPA. It's, the theme of this program was called Game Breakers. I don't know how many of you are very passionate game players on computers, but the idea here is sort of looking at the gaming industry. Computer game developers are very interested in engaging players. So what they want is they want games to be completely balanced so that even after you have played the game for 20 hours or 30 hours, both the players still think that they can win. So the idea is to have a completely balanced game so that no single player has an advantage over the other or has a bias towards winning. And that's one way of maximizing sort of the attractiveness of that game. Taking that idea and adapting it to our mission scenarios, what we want is we want these games to be quickly imbalanced as soon as possible. So if we are going into some sort of an engagement, we want that engagement to end as soon as possible with the probability of winning almost equal to 1. So that was the basic idea behind this program. And the main question was, can we use real-time strategy games? You know, there are a bunch of different games that are available to come up with algorithms or come up with the methods to figure out what's the best way of imbalancing a game. Now, this again ties very well to the mission design problem, but here are the main challenges that we had to overcome in order to come up with that methods. One is that the design space of what are the things that you can tweak is very large in these kinds of real-time strategy games, and that includes things like different kinds of weapons, how much damage does each entity have, how many of those entities, what kind of strategies. So there's a long list of things that we can change. And the second big challenge is that as the game evolves, the state of the game changes very rapidly. So how do you account for the state of the game and the resources that you can change to come up with the optimal sort of strategy. So again, these methods are very useful when we look at simulation environments such as AFSIM, Command, Flashpoint campaigns, and so on that are currently being used in mission design settings. And there were a number of different performers. Purdue was one of the performers, and our solution, we call that an L2J framework, learning to game break. And here is sort of the architecture of that learning to game break approach. And we break it down into 3 layers. The bottom layer is called the player layer. So this is where we are using the AI-based bots who play the games. So there is a lot of research that is going on in using these RTS games to come up with the best AI bots that can win against the best humans who play these games. So that layer basically consists of the set of AI bots that are playing the games. Then we have the tournament layer, which is basically our way of collecting data and understanding understanding the strategy of these bots, understanding what happens if you change different parameters as the input, and we use that to build a database of information that we can then use in the game breaker layer to figure out the optimal strategy of breaking the game as soon as possible. So that's sort of the general architecture. Just to give an example, one of the games that we used was StarCraft 2. We also used a micro RTS game, which is a much simpler version, which was an ideal starting point for this, and I'll talk about that at the end. But here, if you look at the 3 layers, on the left you see the player layer, and there's a list of these different AI bots. This video was supposed to start, but that's okay. Then we have the data collection. So there we used the different approaches from statistics. We used design of experiments to collect data by running these games. And each game was a self-play game. There were 2 bots, identical bots for playing the game. And since the outcomes are stochastic, we ran those games multiple times. And that's how we built our database. And then on the game-breaking layer, we used techniques, model building techniques such as Gaussian processes and convolutional neural networks, CNNs, to take the data and then build a meta model of of the inputs being the changes that we can make to the game, and outputs being probability of winning for each of the players. So that's one of the outputs, and then we also looked at other outputs such as how long does it take to win that game, and that's a quantification of how well we are doing in terms of breaking the game. So ideally, for the player who is trying to break the game, the probability of win is 1, and the time that it takes is very short, or almost 0. So here, what we're doing is we're combining techniques from statistics, combining techniques from AI, particularly convolutional neural networks, and then we are also combining techniques that are developed in the explainable AI community. Particularly, we use the Shapley explanations to explain what are the different parameters that have the biggest impact on the output, which is the probability of win. Because that is what we want to change, because that's going to give us the minimum cost of changing those either weapon systems or capabilities to achieve our objective as fast as possible. Now, once we have developed this model and once we have these meta models using CNNs and Gaussian processes, what are the things that we can do? We can do 3 different things. First is at the pre-mission level. So before the mission has even started, we can assess the impact of using the different portfolios of different weapon systems going in, and we can assess the impact of the different sort of damage that each weapon can do, and look at the parameters and predict the impact on the output. So that's pre-mission. Second is during the mission. Since our neural network model is trained based on the state of the game at different time steps, we can actually look at any state of the game and then predict the probability of winning. And here is one example in the middle. This figure shows over the gameplay. So on the x-axis, we have time during which the game is being played. And then y-axis is player 1's winning probability. And the uncertainty bounds that you see are the uncertainty quantification that we have done on the neural network using MCDN approach. So as you can see in this particular gameplay, up to a certain point about game frame of 60, both the players have almost equal probability of winning, but something happens around here at this time that suddenly player 1's probability of winning goes up. And that's an important thing to observe, and then to try to go back and figure out what was the key decision that was taken at that point in time, what was the key state of the game at that point in time that resulted in this change, because that can give us insight into the strategy and how that strategy affects the probability of winning. So this is during the mission. And then post-mission, we can go back and do a retrospective analysis, saying, okay, given this particular game frame, what were the key parameters that had the biggest influence? And this is where we are using our explainable AI-based techniques like the SHAP values. So here is one sort of higher level tool that we have created for this RTS game. And as you can see, the kinds of things that we can do are these sliders. We can actually change the effect of, for example, air-to-air damage. If we can reduce that, what is going to be the effect? Oh, okay. So what is going to be the effect on the confidence of winning? So we are able to predict the probability of win along with the confidence interval. So in the morning, there was this discussion, what we need is sensitivity analysis. So this is an example of the kind of sensitivity analysis that is useful for mission engineering. And then at the bottom, the bar charts that you see are our gradient estimates, saying what is the effect of these different variables like the ATA damage or battlecruiser health on the particular output that we are interested in. I'll go to the next slide. Now, here, this is intentionally not to be read, but the main idea is these rows are all the different parameters that we can change, and the bars that you see are the Shapley values, which means what the impact of those values on the particular outputs, and we have.
There we go. Okay.
Oh, sorry. So what we have here is each row is the parameter that we can modify, and then the corresponding impact on the output, the corresponding sensitivity on the output, and we have classified it in terms of variables affecting health, variables related to movement speed, variables related to attack speed, and so on. And this is just on the right-hand side top is just a magnified version of a small section of that diagram. And then again, we talked about this figure on the bottom right, which helped us figure out what are the key features that affected the outputs, one being supply and the other being damage rate. So that's, again, the engagement analysis example. And again, we have many, many more such results. So if you're interested, we'll be happy to show some of those outside. There was another big insight that we got while using a simpler game called the micro RTS game. What happened was when we were training these models, even though we are using the same kind of agents, what we found that always one of the players had a big advantage and always had a higher probability of winning. So this seemed like an error in our modeling. We tried to figure out all different ways of fixing our error. But what happened, we actually contacted the developer of the game. What happened was there was actually a bias in the game itself, in the way the different agents were coded, which resulted in this kind of a biased behavior. So an approach like this, the L2J framework, can also help us in figuring out, in designing these simulation environments, or in figuring out whether these simulation environments themselves have inherent biases or problems. So that's another sort of a side benefit that we have from this kind of a tool. And in terms of applications of the L2J framework to the broader AIRC program, of course, there are 4 different applications. One is in acquisition, one is in planning, execution, and in simulation characterization. But the 2 key things for our L2J framework are such a framework applied to a more sort of representative simulation can actually be used to help in make key decisions about the missions, and then in characterizing the simulation and then identifying whether there are any inherent problems with that. So I'll bring it back to Dan. Thank you.
Okay, don't go too far. You'll get all the questions. So just to wrap up here, and we'll have a few moments for questions. So as promised, I wanted to highlight with just a few slides that I'll probably only be able to say a few words about, but fortunately, the originators are here in the audience with us. So some nice work going on at GTRI, and Danny Brown. Danny, wave your hand, is here on some really interesting ways to visualize mission engineering analytics and be sensitive to the subject matter experts that come and go from these studies. And also a study that was completed by the CERC, I think a couple years ago, on mission engineering competencies. And Nicole, you want to wave your hand there? I'll point all questions, even though Dinesh and others were involved, to Nicole Hutchinson in the back. So on Danny and team's work, again, here's just an example of some Bayes networks and probabilistic graphical models. But again, the way Danny explained to me some of the value that they found from these kind of graphical approaches is of course, visualizing these relationships and analytics, but also, again, something probably all of us have faced is you get subject matter expertise that becomes embedded in the model, and then those SMEs go off, especially the military uniformed ones, and go off to their next assignment. And there's sort of a loss in pedigree and heritage of that. And so these models can actually be encapsulate some of that subject matter expertise so that it transitions and is added to by other experts versus just completely lost and starting over again. Danny, I hope that was good enough teaser for others to come and talk to you. So I'll skip a couple of the slides. Just again on the mission engineering competency framework. Here you see some of the data that's probably not terribly, well, it's not too bad from a font perspective. But really, some of the interesting things, if you look at on the right-hand side, the bar chart, you know, a very kind of uneven perception of what people think are their responsibilities in mission engineering. Now, the good news is for most of them, understanding the mission was ranked highest, which is good. But, you know, there's probably a lot of work that needs to be done. We talked about people early on in the day today and then throughout the rest of the day. And so the mission engineering workforce is an important part of the equation. And just the last slide here from the team's work on competencies was this kind of holistic framework of the kinds of things and people and perspectives that are involved. And the way Nicole explains to me, this spider diagram in the middle is just a notional depiction, not a real data message here. But the point is, different people with different responsibilities in mission engineering should have strong suits in some of these different skill areas and not needing to be expert in sort of the outer data point on all of them. So I think there's a lot more detail in the mission engineering competencies report that I encourage you to take a look at. All right, that's it for us. Happy to take a few questions. Thank you.
What was the main finding on the imbalancing? What did you learn, like a couple takeaways from that?
So clearly one of them was that some games have inherent imbalance because of the way these agents are working or because of the way the game itself is structured. And the second one was through our framework, we were able to identify strategies that can either imbalance or balance the game in the minimum cost possible.
What were some of those strategies?
So some of those strategies included increasing the damage of certain specific types of, let's say, weapons in the game, and those findings were sort of tied to the specific bot that we used. So, for example, if we are using these RL-based, sophisticated bot, then there were different kinds of weapon systems that were more important based on the strategy followed. Whereas if we are using a simple sort of a rule-based agent, then there were different kinds of weapons. Again, it was completely strategy dependent.
I would just add that what DARPA is really excited about taking this stuff forward is thinking about the wargaming exercises that go on and how important those are, but how difficult they are. As it was explained to us by an Air Force expert wargamer, I mean, these are year-long events with mostly human beings making decisions, and it produces kind of like one data point at the end with very little connection to the chain of decisions that produce some of those outcomes. And so I think you'll see more activity in this kind of area from DARPA shortly. Certainly we're hoping there is. Other questions?
So on the DSF work, I liked how you kind of rolled it up to just like risk versus cost. Was that risk aggregation, was that something configured by the user? Was there like a way to do sensitivity based on how you came came about to whatever that quantitative measure was?
So yes, and there's more to the story. So that remember I said there's multiple mathematical programs that you can do. Some of them, sort of that risk is just an accumulation of the uncertainty in the different systems and interactions, so it's more of a traditional kind of probabilistic analysis. Mm-hmm. But in the one we're showing here, that risk aversion factor is user selectable. And so you select your risk aversion level, and that changes the family of portfolios that lie on the efficient frontier.
Okay,
Yep.
all right, thanks.